Imagine a world where your computer processor isn't made of silicon and circuits, but of living, breathing human tissue. It sounds like a scene from a dark sci-fi thriller, but inside this small, unassuming box, the unthinkable is happening. This isn't science fiction. This is the CL1. Inside this unassuming box sits a microchip called a multi-electrode array. But the hardware isn't the story, it's the wetware. Layered onto this chip are roughly 200,000 living human neurons. These cells are alive, they are communicating, and today they are doing something no one thought possible for a cluster of cells in a dish. They are entering the digital hellscape of doom. In the history of computing, we have always sought to mimic the brain. We built neural networks and artificial intelligence to simulate how we think. But at Cortical Labs, we asked a different question. Why simulate the brain when you can use the real thing? Deep inside a high-tech chassis, past the cooling fans and the circuit boards, sits a small glass window. Inside that window is a solution of synthetic nutrients, and inside that fluid, something is waking up. This isn't a traditional CPU. This is the CL1. It houses roughly 200,000 living human neurons fused onto a microchip called a multi-electrode array. For the first time in history, we aren't just building computers that act like brains. We are looking at a computer that is a brain. Last year, the world watched as these biological cells learned to play Pong. It was a milestone in real-time goal-directed learning. But Pong was simple. A ball goes up, a paddle goes up. It was a direct, predictable mirror. But the team at Cortical Labs wanted to push the boundaries of what biological wetware could actually handle. They didn't want a mirror, they wanted a trial by fire. They decided to see if these cells could survive the chaos of 1993's most iconic 3D shooter. They wanted to see if living tissue could navigate the corridors of doom. To do this, they didn't just write a program, they built a bridge, and they brought in a specialist, an independent researcher named Sean, to prove that the era of biocomputation isn't just coming, it's already here. The challenge Sean faced was immense. Doom is entropy. It is 3D space, enemies, and exploration. Unlike the team's previous work with Pong, there is no direct relationship between the input and the output. Sean's background as a researcher focused on exactly this, how to map complex, noisy environments into a format that biological cells can actually understand. In the past, this kind of systems integration took years. The original Pong experiment required 18 months of grueling hardware and software calibration just to get a single hit on the ball. But Sean didn't have 18 months. He had the new Cortical Labs API. Simply put, the CL1 API is the software bridge between your computer and a dish of living neurons. The CL1 is a hardware unit, a biological computer that houses about 200,000 human brain cells growing on top of a silicon chip. The API is the set of tools that lets you, as a programmer, talk to those cells. The really clever part is that the API is built for Python developers. If you know Python, you can start working with this technology. Cortical Labs provides an SDK, a software development kit, that implements the API. This kit even includes a simulator. That means you can download it right now, write code, and watch how a simulated neural network would react, all without needing access to a $35,000 biological computer. It's like having a virtual petri dish on your laptop. But to understand what the API actually does, let's look at the famous experiment where researcher Sean Cole used the CL1 to play the video game Doom. The API handles two critical jobs: input and output. First, the API translates the game screen, what the neurons need to see, into patterns of electrical stimulation. It's like the API is whispering to the neurons, telling them what's happening in the game world. Second, when those neurons respond, they generate their own electrical activity. The API listens for that activity, records it, and then translates those biological spikes back into digital commands. In the case of Doom, that meant moving left, right, or shooting. The entire loop, send the visual data, wait for the neurons to think, and convert their response into a keyboard press, happens in real time through the API. When you watch the footage, you aren't seeing a world-class speedrunner. You are seeing a beginner. The cells play like someone who has never seen a computer. And in all fairness, they haven't. They spin, they get stuck, and they die a lot. But they are showing evidence of learning. They are seeking out enemies. They are reacting to the environment. They are proving that biological tissue can navigate a 3D virtual world. The researchers at Cortical Labs have officially solved the interface problem. They have built the pump systems, the activity windows, and the API that allows anyone from anywhere in the world to talk to these cells in real time. The hardware is no longer the limit. Now, the limit is our imagination. The cortical cloud is open. The neurons are ready. Sean and the team have laid the foundation. Now, they are challenging the global community of developers and researchers to take over. They've shown that a dish of cells can play Doom. The only question left is, what will the world teach them next? Tell me, what do you want to teach those neurons? Do you think it's going to beat the silicon computer? Are we able to see one day ChatGPT built from the cells of our brain? Write me on the comments. See you on the next one.